Hi again. Continuing our review for Module 2, we reached the understanding that Navier-Stokes equation plays a major role in many problems that we have seen in this module. We also reached the conclusion that dimensional analysis and Buckingham pi theorem can help us understand the problems in a relatively meaningful manner. As I said before, nature really doesn't work in terms of feet or inches or yards. Nature and physical laws in nature don't have units, and they speak in dimensionless parameters. So we better learn those dimensionless parameters if we want to understand how nature works. Let's take Navier-Stokes equation. What we did in terms of parameters and making things dimensionless should also be applied to equations of motion, such as Navier-Stokes equation. If we take the length scale for a problem, for example, like a sphere falling down in a liquid with density ρ and viscosity μ, we can take the length scale of this sphere, the radius of it, for example, r, and call that L. Then in the Navier-Stokes equation, wherever we have a derivative that has a spatial gradient, like for example dvx over dx or dp over dx, the length scale over which things are varying, the length scale over which things have a significant change in their value, should scale as L. And physically this makes sense. If I'm a fluid element very far from this object, here I probably don't feel any gradient, any change. It's only few radius or diameters around this object that fluid elements start to feel the motion of this object. So that would set the length scale over which the problem feels a significant change in parameters involved. So when we take d over dx term derivatives, really that's the scale for x that we have. Velocity probably will scale between something that goes to almost zero, very far from the object, and things that are probably proportional to the speed of the sphere. So the range over which velocity is changing should scale as u, which is set by the velocity of the falling sphere. The time scale of this phenomenon is probably something that goes as a ratio between the length scale and the velocity scale, L over u. That would set the time scale in this phenomenon. We really don't know what says pressure, what is the scale for pressure yet. But what we can do is assign it some name, PC, and then carry on and see what Navier-Stokes equation will give us. If you look at your notes, after making things dimensionless and defining things, for example, dimensionless parameters such as v star, which was defined as a vector being vector v normalized by the scale for velocity u, or for example x star, which is the normal vector, position vector x normalized over L. If we do this and simplify Navier-Stokes equation, the final equation that we get in the dimensionless form becomes d of v star dt, the acceleration term on the left-hand side, and this is dt star. Everything involved here is dimensionless. So t star would be t divided by the scale of the time scale, which is L over u as mentioned here. The right-hand side would be the gradient, grad star, which means that it's not normal d over dx terms that we need there. It's d over dx x star terms, which x star is x over L that are involved in grad operator. So the the dimensionless version of the grad operator acting on the dimensionless pressure, P star, plus there's a 1 over Reynolds based on length scale L that emerges, and then Laplacian of the velocity in the dimensionless form, and the final term, which is the dimensionless version of the gravitational or body forces, which is 1 over Froude number multiplied to Ez. And for your memory, you can check your notes. Froude number is defined as g times L divided by u squared. And more important than that is the Reynolds number based on L, which is defined as rho u L divided by mu. If we think about the physical nature of this Reynolds number, a dimensionless group, it is indeed the scale of rho u squared over L, which is the dominant or the significant scale of terms on the left-hand side of Navier-Stokes equation. It's the scale for inertial terms, normalized over scale for viscous terms, which go as mu u over L squared. You can see that the L squared here goes to the top, u cancels, and you get rho u L over mu. So indeed, Reynolds number is really showing the ratio of terms from left-hand side when you compare their scales with respect to terms on the right-hand side, which are the viscous terms. So you take the inertia terms, you normalize them over viscous term, their ratio would give you the Reynolds number. This understanding, combined with this dimensionless version of Navier-Stokes equation, can help us understand things in a better way. And in a moment, we will show that. Let's take the limit of Reynolds going to infinity. So if Reynolds number is going to infinity, so if I take the limit of Reynolds based on L going to infinity, this term vanishes because it's 1 over infinity, it completely goes away. Physically speaking, you take the ratio of inertia terms over viscous terms and it's going to infinity, which means that viscous terms are completely negligible compared to inertia terms. In that limit, we actually see completely this term vanishes, and in the dimensional form, we recover back what we had as Euler equation. Rho dV over dt is equal to gradient of the pressure plus rho g term. And this simply suggests that there's no viscous term involved anymore, so pressure on the right-hand side should scale with things on the left-hand side, and that's simply this scaling between these two terms. So this guy and this guy, they should scale like each other. And that suggests that scale for pressure, PC, normalize over length scale because it's gradient, PC over L, should scale as rho US squared over L, which suggests that PC should scale as rho US squared. So this is the Reynolds number going to infinity that is simply suggesting to us that viscous terms are completely negligible and pressures involved in the problem have a characteristic scale. That characteristic scale is set by the inertia of the fluid elements, and it goes as rho US squared. It's the kinetic energy per unit volume. That's really what sets the scale for pressure. On the other hand, you can also think about the other limits when Reynolds goes to 0. If Reynolds goes to 0, this term is 1 over 0, so it's blowing up. It's becoming the dominant terms. It's becoming much more important than whatever you have on the left-hand side. In other words, the ratio of inertia terms over viscous terms is going to 0, so inertia terms are really negligible compared to viscous terms. And if you want to really think about the original dimensional form of Navier-Stokes, it tells us that the left-hand side is approximately 0. What you have is just the gradient of the pressure plus viscous terms, which go as mu del 2 velocity, plus gravitational forces per unit volume, which go as rho g. And this simple idea this time suggests a new scaling. Suggests that this time these terms, the viscous terms and the pressure gradient, should scale with each other. And if that's the case, I can continue probably right at the bottom here. If that's the case, this tells us that mu u divided by L squared should scale as the characteristic pressure divided by L. And in simple words, in this case, the characteristic pressure scales as mu multiplied to u divided by L. So we see that the same problem in two different regions, in two different limits of Reynolds number, shows different characteristic scales naturally emerge for pressure. At very large Reynolds number, pressure scales with the kinetic energy of fluid elements per unit volume, which is captured by rho US squared. At very low Reynolds numbers, pressure really is set by the scale of viscous terms, and that goes as viscosity times a shear rate, which is set by the velocity gradient, which is u divided by L. These two different scalings can definitely help you understand different regimes of different flows. For example, let's take the case of a Stokes flow. So a Stokes flow regime, which is, maybe I should use the different color. A Stokes flow regime, which is the limit where Reynolds number is much smaller than 1, is a case where viscous effects are dominant and inertia is not anymore anything to really bother with. In this case, if I want to, for example, predict what is the drag force that a falling sphere in a viscous liquid feels, I can easily do that in 2 lines of scaling. I can write down that the drag force should scale as a characteristic pressure multiplied to a characteristic area, which is r squared. And if I am at the limit of low Reynolds numbers, that characteristic pressure should go as viscosity times velocity divided by L. So that goes as mu u divided by L, which is the same as r multiplied to r squared, which tells me that the drag force should scale as mu u multiplied to r. So this scaling is something that you can easily get. And if you look at your solution of Stokes flow past the sphere, actually, in your notes, you see that you're not that far away. The real exact solution, so if you like the real exact solution, would be something that goes as a 6 pi multiplied to mu u r. So you do a lot of algebra to really find this prefactor, numerical prefactor, to be equal to 6 times pi. But if you just use the idea of scales involved and the fact that you are at the limit of low Reynolds numbers, you can easily get the correct value without doing all that algebra. This is an interesting concept, and I hope you can easily manipulate Navier-Stokes equation in different problems, and based on the limit of Reynolds number, think correctly about what really is setting the scale of pressure or shear stresses or velocities in the specific problem that you are dealing with. Now, as an exercise, you can think of the large Reynolds number case of this problem. When Reynolds number is much larger than 1, that pressure is not anymore set by viscous terms, but on the other hand is set by inertia terms. So it goes as rho u squared. If you have that, then you can actually guess what would be the form of the drag force at the large Reynolds number. If you have the form of drag force at both low and large Reynolds numbers, then maybe you can ask what will happen to drag coefficient, which is the dimensionless group that captures the drag force that an object feels as it's moving in a fluid of a given density and viscosity. All of these concepts have been covered in Module 2. I really encourage you to go back and look at some of those videos to see how these subtleties work. Before moving forward, I just want to mention one final thing for the limit of very low Reynolds number, which is Stokes flow. We also notice that in this limit, the flow or the solution to the flow has certain properties. So one property is uniqueness. The solutions are unique in this limit. That means once you find a solution, that solution is the solution. You cannot have 2 solutions in the limit of Reynolds equal to 0. You can only have one solution, and the solution exists. This solution exists and is unique, and it also has minimum dissipation. The other property of Stokes flow was the fact that the solutions are linear, because as we discussed before, in the limit of 0 Reynolds number, when the left-hand side doesn't exist anymore, all the nonlinearities, they disappear, and whatever terms are left on the right-hand side are linear. So if you have a solution 1 to the Stokes problem, and you have another solution 2 to the same equation but different boundary conditions, you can sum them together and you get a combined solution that satisfies combined boundary conditions. The final property of these Stokes flow problems, which is actually interesting, is what we call kinematic reversibility. And that's also a consequence of the fact that inertia terms completely vanish. To show that consequence and to show really what that kinematic reversibility means in the limit of low Reynolds number flows when we reach almost 0, approximately 0 contribution from inertia, and you only have pressure gradient, viscous terms, and gravity balancing each other, we need to look at the demo, which really displays this idea of kinematic reversibility. And that's what we will cover in the coming video. But again, to keep in mind, when we talk about a Stokes flow, means Reynolds is much smaller than 1 that we can almost assume that the governing equation, the momentum equation, has 0 for the value of the inertia terms on the left-hand side. As a consequence of that, the kinematic reversibility will be displayed in the next video.